from Group B are going to share about the evolution from classical to quantum particle system, the classical particles, the boson particles, the fermionion particles, and the differences between Maxwell-Boltzmann, Fermi-Dirac, and Bose-Einstein. First and foremost, I will simply explain about the evolution from classical to quantum particle system. So, since the electrons are identical from each other, the wave function of an atom with more than one electron must satisfy special conditions. The problem of identical particles does not arise in classical physics, where objects are large and always distinguishable, at least in principle. The global wave function, psi, of a system of identical particles depends on the coordinates of all particles. If the coordinates of two of the particles are inverted, then the wave function must remain unchanged or at most change sign. A change sign is allowed because it is psi squared that interferes with the physical interpretation of the wave function. The symmetry of the wave function for identical particles is closely related to the spins of the particles. In quantum field theory, particles with half-half spin can be shown to have anti-symmetric wave functions. Particles with zero or total spin have symmetric wave functions and are called bosons after the Indian mathematician and physicist called Satyendra Nath Bose, who first applied the idea of photon symmetry in 1924 to 1925. The claim of anti-symmetric wave functions for fermions led to a fundamental result known as exclusion principle, first proposed in 1925 by the Austrian physicist Wolfgang Pauli. Therefore, two electrons in the same atom cannot have the same set values for the four quantum numbers, which are n, l, m, and ms. The exclusion principle underlies many properties of matter, including the periodic table of the elements, the nature of chemical bonds, and the behavior of electrons in solids, which in turn determines whether the solid is a metal, an insulator, or a semiconductor. Each electron has its own wave function called an orbital. The global wave function for all electrons in an atom satisfies the exclusion principle.
A classical particle is a point-like object and obeys the rules of Maxwell-Boltzmann statistics. Maxwell-Boltzmann distribution used to investigate the molecular speed or velocity. James Clerk Maxwell in 1859 determined the distribution velocities among molecules of gas. It was later generalized in 1871 by Ludwig Boltzmann to express the distribution of energies among the molecules. The type of particle is defined by properties that define how it interacts, like mass, gravity, and charge electromagnetism. Next, particles are distinguishable and obey Pauli exclusion principle. There are no restrictions on how many particles can be put into any one state simultaneously. Any number of particles can be in any state. Example, we have 3 particles and 2 subcontainers. So, how many arrangements of n particles in these G subcontainers are possible? There will be 8 possible arrangements of particles. Therefore, if our system has a particular state that has a particular degeneracy, there is an additional multiplicity for that particular state. This Maxwell-Boltzmann statistics depends on temperature. Particles are spinless, and the total number of particles in the entire system is constant. Besides, a new microstate is obtained when interchange of the particles. Here are some other formulas related to this topic.
Boson particle. What is actually boson particle is? Boson is a particle that obey the rules of Bose-Einstein statistics but not obey the Pauli exclusion principle. And it's sometimes called as quartz particle because boson able to control the interaction of physical forces like electromagnetic forces. Okay, next is boson have a quantum spin contain an integer value like 0, 1, and 2, and it's very different from Fermi ion because Fermi ion have a half spin. Okay, next is boson come from the surname. The name boson is come from the surname of Indian physicist Sayendranath Bose, who is worked with Albert Einstein in the early 20th century to develop a method of analysis called Bose-Einstein statistics. In order to fully understand Planck's law, which is the thermodynamic equilibrium equation that come up from Max Planck's work on the black body radiation problem, Bose first proposed that the method in a 1924 paper trying to analyze the behavior of photons. Then he sent the paper to Einstein to make sure the paper get published. One of the dramatic effects of Bose-Einstein statistics is the prediction that boson can overlap and coexist with other bosons. On the other hand, Fermi ion cannot do this because they follow the Pauli exclusion principles. Because of the prediction, it is possible for the photon to become a laser, and some matter is able to form the exotic state of Bose-Einstein condensate. Okay, according to the standard model of quantum physics, there are a number of fundamental bosons which are not made up of smaller particles, including basic gauge boson. As we can see in the figure, we have a gauge boson and Higgs boson. Okay, gauge boson have a quantum speed equal. Gauge boson have a quantum spin equal to 1, and there are 4 types of gauge boson, which is first photon. Photon known as a particle of light, and it carry all electromagnetic energy, and it acts as the gauge boson that mediates the force of electromagnetic interaction. The second one is gluon. Gluon mediate the interaction of the strong nuclear forces where it's bind together quarks to form proton and neutron, and also hold the protons and neutron together within the atom's nucleus. The third one is W boson. The W boson have a charge, and it involved in mediating the weak nuclear force. And the last one for the gauge boson is Z boson. Z boson also have a 2 gauge boson, which means it's a charged boson, and it also mediates the weak nucleus force. And finally we have Higgs boson. Higgs boson have a quantum spin equal to 0.
In particle physics, a fermion is a type of particle that obeys the rules of Fermi-Dirac statistics, namely the Pauli exclusion principle. This fermion also have a quantum spin which contain a half integer value, such as half, negative half, and negative third half, and so on. Fermions are sometimes called matter particles because they are the particles that make up most of what we think of the physical matter in our world, including protons, neutrons, and electrons. Fermions were first predicted in 1925 by the physicist Wolfgang Pauli, who was trying to figure out how to explain the atomic structure proposed in 1922 by Niels Bohr. Bohr had used experimental evidence to build an atomic model which contained electron shells, creating stable orbits for electrons to move around the atomic nucleus. Though this matched well with the evidence, there was no particular reason why this structure would be so stable and the explanation that Pauli was trying to reach. He realized that if you assign quantum numbers to these electrons, then there seemed to be some sort of principle which that no two electrons could be in exactly the same state. This rule became known as the Pauli exclusion principle. There are a total of 12 fundamental fermions, fermions that are not made up of smaller particles, that have been experimentally identified. They fall into two categories, quarks and leptons. Quarks are the particles that make up hadrons, such as protons and neutrons. There are such as up quark, top quark, bottom quark, down quark, charm quark, and strange quark. While 6 types of leptons are electron neutrino, muon neutrino, and tau neutrino. Beyond the fundamental fermions, another class of fermions can be created by combining fermions together, which is possibly along with bosons to get a resulting particle with a half-integer spin. The quantum spins add up, so some basic mathematics show that any particle which contains an odd number of fermions is going to end up with a half-integer spin, and therefore will be a fermion itself. Some example includes baryons and also helium-3.
We are going to discuss about on how the three types of statistics, natural movement, Bose-Einstein, and Fermi-Dirac, influences the possible state of the system. First of all, Maxwell-Boltzmann. Maxwell-Boltzmann is a statistic applicable to identical and distinguishable. The molecules of gas are particles of this type. Then, for Bose-Einstein, it is a statistic applicable to the identical and indistinguishable, which is different than Maxwell-Boltzmann. These particles are called bosons, for example, photons and helium atoms. Therefore, for Fermi-Dirac, it is a statistic that applicable to the identical and indistinguishable, same with Bose-Einstein. Such example, electron and photon. Maxwell-Boltzmann is applied to classical particles with non-quantized energy level. It turns out these are not any truly classical particles, which it can be any type of spin. But Maxwell-Boltzmann statistic is still a good approximation in many cases. And for the wave function, they do not overlap. However, for Bose-Einstein, it is applied to a quantum particle with the property that any number of particles can occupy any level. It turns out these are the particles of zero or with integral spin, like 0, 1, or 0. Unlike Maxwell-Boltzmann properties, this statistic do have overlap of the wave function. Then, for Fermi-Dirac, it seems with Bose-Einstein as it also applies to quantum particles, but with the property that only one particle can occupy any particular level. This particle obeys Pauli exclusion principle. It turns out these are the particles with half-integral spin, like 1/2, 3/2, and 5/2. Same with Bose-Einstein, they are overlapping for wave function. And lastly, for distribution of function, as we know, the equation is A exponent power E by kT, where E is the energy and K is volume constant. So for these three statistics, they are using the similar equation except for Bose-Einstein, where it is 1/A exponent power E by kT minus 1, while for Fermi-Dirac it is 1/A exponent power E by kT plus 1. I think that's all from us. Thank you.